Hello everyone. In this video, I'll introduce system of simultaneous linear equations and show how to solve them using the Gauss elimination method. Many practical applications of engineering and science lead to a system of linear equations. For example, fluid flow solving for reactions or moments in a complex truss problems or heat transfer. We are involving with the system of simultaneous equations. Let's look at the two examples, okay, that is related to the small systems. The first example is about the electrical network, okay, and this electrical network consists of the 6 resistors, and if the voltage at node 1 and node 6 are specified as a 200 and 0 volts, we should determine the voltage at node 2, 3, 4, and 5. For finding the voltage at these 4 nodes, okay, we can apply the Kirchhoff law. As we know that based on the Kirchhoff law, the summation of the current arriving at any nodes must be equal to the 0. If we apply or if we write the sum of all the current arriving at the node 1, we have this equation. There is a one current from node 1 to, okay, this is another current, and this is the next current that arriving to the node 2. And the summation of these 3 currents should be equal 0. Also, we know that the I or currents equal voltage over resistance. And we have informations about all the resistance of the system, all the resistor of the systems. For this reason, we can write here, okay, and at the top we have this equation. Exactly, we will write the sum of the currents arriving at the node 3, okay, and as you can see at node 3 we have 2 current arrivings, one of them from here, this is another one, okay, and again when we apply the Kirchhoff law for the node 3, we find the next equation, and we exactly apply for the node 4 and 5, okay, and now we have 4 simultaneous linear equations, okay, with 4 unknowns, and our unknowns is a V2, V3, V4, and V5, okay, and when we solve these problems, okay, this system of equations, we can determine the voltage at each of these nodes. Another example is about this system. This system consists of 3 rigid bars with 6 wire ropes, okay, that support these 3 loads, P1, P2, and P3, okay. We should find the tension in these 6 ropes, okay, and the value of the P1, P2, and P3 is not. For finding the tension for these 6 ropes, okay, we can apply the equation of equilibrium for each bar separately. First, we start for the bar 3, okay. In a bar 3, we have 2 tensions, okay, and this is about the force of P3, and this is about the first equations for the bar 3. The next equilibrium equation that we can apply for the bar 3 is try to determine the moments, okay, on the, for example, for this example, for the left side of this bar. And we consider the clockwise as a positive rotation, okay? And when we apply this equation, it means the summation of the moment at this point should be equal 0. We have P3 times 1 minus, this is as a counterclockwise, minus T times this distance as a 4. Also, we can apply the equation of equilibrium for the bar too, okay, but it's very important to write or draw the reaction of the tensions at the cable E because the system in the equilibrium conditions. This is again all the equilibrium equation for bar 2 and this is for bar 1. When we are writing these 6 equations, now we have 6 simultaneous equations with 6 unknowns, and we can solve these problems and find the tension at each of these ropes. This is the 2 examples, okay, and these examples for this small system of equation. When the number of the equation less than the 2000, we can say we have a small system. But we often have a problems with large system of equations. It means the number of equations larger than the 2000, often in tens of millions of unknowns when analyzing the fluid flow mechanical response of structures by utilizing finite volume methods, finite elements method. And again, the N is talking about the number of simultaneous equations. For example, look at these examples. Okay, in this example, FBM computations of pulsatile flow and LVAD flow in an adult 60 years old male ascending aorta and coronaries. Okay, for solving these problems, okay, we are involving with the 6 to 10 millions unknowns. For this reason, this is considered as a large system. This is another examples, okay, for the heat transfers. And as you can see, for these examples, we are involving with 10 millions unknowns, okay, when we make it the mesh on the surface of this object. For this reason, for solving these equations, okay, we can solve by direct methods when the number of the equation less than the 2000, okay, and when the number of the equation larger than the 2000, we have to switch to the iterative method. We will cover and apply concept of linear algebra as we explore this topic. Okay, look at this example. We have in these problems, okay, we have 3 planes, okay, and we can say we have 3 simultaneous equations, okay, and we are trying to solve these system of equations. As a general, when we want to solve this type of equation, we have to write it based on matrix and vectors, okay? And after that, we can solve this system of equations, okay? Look at these 3 equations. If we are writing all the coefficient of the x-axis, y-axis, and the z-axis in the matrix 4, okay, we can say the first column of this matrix represent all the coefficients for the x variables. The second columns represent all the coefficients for the y components or the y variables, and this is about all the coefficients for the third variables, that is as a z. This matrix is called matrix of the coefficients, okay, and always as a square matrix. How about this one? This is the map and vector of the variable, okay, x, y, z, okay, and the dimension always is n times 1. How about these vectors, and how about these constant value on the right side is meaning 10, 12, and minus 1. This is called right-hand side vector, okay, and this is as a vector. Okay, this is the first step for solving the system of linear equation. And again, this is the matrix of the coefficients x and b as a vector. Why we say, okay, why we consider the b as a vector? Let me to show you the reason. For example, when the matrix A pre-multiply the vector x, produce another vector b. For example, look at this figure. We have a vector of the x, and on the right hand side in this figure or in this graph, the magnitude and direction of the x totally changed because the matrix of the A pre-multiplied to this vector, okay, and generate the next vector. For this reason, this is the B as a vector. Look at these examples. We have the vector A. We have a vector x. The value is a 1, 1, and say 1, 1. When the matrix A pre-multiplies the vector x, and it generates a new vector by rotating and stretching its magnitude, okay? Because this is the matrix A and this is the vector x, and when the matrix A pre-multiply to this vector, rotation and stretching in a magnitude is happen and generate this vector. If we have a matrix B, and when the matrix B pre-multiplies vector x, this means 1, 1, it generates a new vector by rotating it and shrinkaging its magnitude. This is about why the result of matrix times vector become as a vector. This is related to the linear transformations. What's the meaning of the linear transformation? A linear transformation takes vectors and turns them into the new vector, okay? For this reason, when the matrix operates on a vector, produce another vector, and this is called linear transformation. Can also think of solving the problem ax equal b as a follows. This is about all the coefficients for the x1, and this is about the coefficients for the second variable, it means x2. We can write the coefficient of the x1 in this format, and this is the coefficient for x2. Find the combination of the columns of A, produce the B. Okay, and this condition happens when the vector A and B is linearly independent. Let me to show you what's the meaning of the linearly independent. First, look at the example 2. The example 2, if you look at the third equation is a combination of the equation 1 and equation 2. For this reason, these equations are not independent and doesn't have a unique solution. And if you try to find the determinant of this coefficient, the matrix of the coefficient, the answer will be 0. How about the example 1? We cannot, all of these equations, okay, is independent, okay, and we cannot write one equation as a combination of other equations, okay. For this reason, this system is called linearly independent, okay, and the determinant of a matrix of coefficient is not 0, and you have a unique answer for this system of equations. Okay, as you can see, for solving the system of linear equations, we are involving with the matrix. Let's quickly review the matrix operations and properties before solving simultaneous system of equations. If we have a matrix A, the dimension of this matrix 2 by 2. 2, the first number is representing the total row for this matrix, that is 2. And the second number, okay, for the dimension is talk about the total number of the columns for the matrix. For this reason, for the matrix A, we have a 2 columns and 2 row and 2 columns. For this reason, the dimension 2 by 2. For add and subtract, the two matrices should have the same dimensions if we are adding A and B. How we add these two matrices? Terms by term, okay? For example, for finding the first element or first term in the matrix of A plus B, we add A1 to the B11. How about these terms? We are adding this element to this element. We can say A plus B equal B plus A, but A minus B is not equal B minus A. Another one is about the multiply. For the multiply, when we the matrix A pre-multiply to the matrix B, we can find each terms of this matrix in this way. For example, for the first terms or first element at the matrix of A times B, we have the first row of the matrix A times the first column of the matrix B. And this is for the other element. If the matrix of the B pre-multiplies the matrix A, okay, in this case, for example, for finding the first element of this matrix, we have to multiply the first row of the matrix B to the first column of the matrix A. And this is for other elements of this matrix. Okay, let's look at some examples, okay, that show the different operations in the matrix. Okay, we have the matrix A. This is the matrix A. The matrix A is 1, 2, 3, 4. Okay. And this is the matrix B is 4, 5, 6, 7. What is the dimension of this matrix? We have a 2-row and 2 column. For B, 2 by 2. If we are trying to find the matrix of A plus B, we have 1 plus 4, 2 plus 5, 3, this is plus, okay? 3 plus 6, 4 plus 7. And the answer is 5, 7, 9, 11. How about the A minus B? For the A minus B, we have 1 minus 4, 2 minus 5, 3 minus 6, and 4 minus 7. And the answer will be minus 3, minus 3. Okay, the next one. A times B. What is the meaning A times B? For finding the first element, we have to multiply the first row of the matrix A to the first column of the matrix B. We have 1 times 4, 2 times 6. For finding the second element, first row of the matrix A times the second column of the matrix B. 1 times 4, 1 times 5, plus 2 times 7. For this element, first row times the second row times first column. We have 3 times 4, 4 times 6, and for finding this element, second row times second column. And the answer of A times B, we have 16, 19, 36, 43. But if we are trying to find the B times A, the sequence will be changed. Okay, we have to pre-multiply the matrix B to the matrix A, and the answer of the matrix will be 19, 28, 27, and 40. As you can see, A times B is not equal B times A. That is show the matrix, okay, is not commutative. This is about the solution, okay. This is about the sum property of the matrix. A times B is not equal B times A, is meaning not commutative. A times front is B plus C. We can write A times B plus A times C. This is about talking about the distributive property. And for multiple of these 3 matrices, okay, we can write in this format. This is related to the associative property of the matrix. Another definitions is about the transpose, and the transpose is meaning we are switching the rows and the column of the matrix A. We can say this is the transpose of the matrix A because as you can see, the first row of the matrix A is right or switched to the first column of the matrix, okay? And another useful property, the transpose of the matrix A times B, we can write the transpose of the matrix B times the transpose of the matrix A. Look at these examples. We have this matrix, the matrix of the A. If we are trying to write the transpose of this matrix, the first row switch to the first column, write 1, 2. And the second row of the matrix A is right in the second column of the transpose. It means 3 and 4. And transpose of A times B, this is the answer for the matrix of A and B. As you can see, this value is equal to the transpose of the matrix B times transpose of the matrix A. If you have a matrix of 3 by 3, how we can write the transpose? Again, switch the first row to the first column, 1, 4, 7. The second row switch to the second column and become 2, 5, 8. And the third row switch to the third column, 3, 6, 9. And this is called transpose of the matrix A. Another property another definition is about the inverse of the matrix. The inverse of the matrix A times matrix A equal I. What is the I? Is the identity matrix. In the identity matrix, all elements on the main diagonal is meaning from the top left to the bottom right are all as one, okay? And off diagonals elements are 0. Or we can say all other elements are 0 and A times I equal I and I times A equal I. It's meaning the identity matrix doesn't change the value of the matrix. And as a general, we cannot find the inverse of the non-square matrix. This is about the identity matrix, okay? I times A and A times A, as you can see, it doesn't change the value of the matrix, and identity matrix exists for non-square matrix, depends on the order of multiplication. For example, we have the matrix of the B. The dimension of this matrix is 3 by 2 because this matrix has 3 rows and 2 columns. If we write the B times I, we should use the I by dimension of 2 by 2. But if you try to write or find the I times B, the dimension of the identity matrix must be 3 by 3. But as a general, as you can see, it doesn't, when the identity matrix multiple to the matrix, it doesn't change the value of the matrix. This is the method for finding the inverse of the matrix A 2 by 2. We have 1 over determinant of the matrix times we have to switch the elements in the main diagonals, AD is switched to the DA, and multiple B and C to the negative sides. After that, we can find the inverse of this matrix. For example, if the matrix A is 1, 2, 3, 4, this is the inverse of this matrix. And when we multiply these two matrices together, we should get the identity matrix. This means 1, 1, 0, 0. 1, 0, 0, 1, sorry. And again, we cannot invert a non-square matrix. This is another useful property in the matrices, okay? The inverse of the matrix A times B is equal the inverse of the matrix B times inverse of the matrix A. And how we can find the determinants? The determinant of the matrix 2 by 2 is found by this way. The elements in main diagonal multiple to each other minus the A12, A21. This is about the determinant of 2 by 2, and this is about the determinant of 3 by 3 matrix. For example, if the matrix of the A is 1, 2, 3, 4, the dimension of this matrix 2 by 2, and the determinant of this matrix is a 1 times 4 minus 2 times 3, and the value of the determinant is minus 2. This is some examples, okay, that try to show the different property of the matrix. This is the matrix A, and this is about the inverse of this matrix. When we pre-multiply the inverse of the matrix A to A, the answer as an identity matrix, and A pre-multiply to the inverse of the matrix. Also, we get identity matrix. And about this part, the inverse of A times B, the answer this matrix. And if we are trying to use the property of the matrix and write the inverse of the B times inverse of the A, as you can see, we get the same results. And another useful property, the transpose of A times B is equal transpose of the B times transpose of the matrix A. And as you can see, again, we get the same answer. Okay. By applying the property and operation of matrices discussed in the previous slides, now we can find the value of the vector x. Okay, again, the A is a matrix of the coefficients. The vector of the x is about the vector of all the variables that we have to find it. And B is the right-hand side of the simultaneous system of equation and as a vector. If we pre-multiply these equations by inverse of the matrix A, okay, we get this one. I times X equal the inverse of the matrix A times B. This is the formal solution, okay, for finding all the variables of the vector x. But we never do this in practice. Okay. Can you always solve the ax equal b? No. We can only solve if the inverse of the matrix A exists, and this is assured if the determinant of A is not 0. Okay, let me to show you first graphically, okay, and then I go through the numerical procedure again for finding the x. Okay, first we have to check the determinant. If the determinant of matrix A is not 0, is meaning we can find the inverse of this matrix, and later we can find the value of the x. Okay, look at this graph. In this graph, these two lines with two different slopes, M1 and M2, intersect at a single point, okay, and giving a unique solution. If you are trying to write the equation of the lines, okay, for equation of the lines for these two lines, we have x2 equal m1 x1 plus b1. And the equation for the line 2 is x2 equal m2 x1 plus b2. If we are trying to rewrite in the format of system of equation, is meaning all the variables bring to the left side and the b just keep on the right side. In this case, instead of to write the minus m1 or minus m2, okay, we show by a11 and a21, okay. Now we are trying to write the matrix of the coefficient for these two equations of the line. We have a11, a21. This is all the coefficient for the x1 variables, and the coefficient for the second variable is mean the x2 is 1, 1. We know that these two lines has two different slopes, okay. For this reason, when we determine or when we try to find the determinant of this matrix, the value is not 0. And as you can see, we have a unique solution for this problem. But how about this graph? Again, there is a two lines, but in this graph, these two lines are parallel, okay? And again, we are applying the equation of the lines for these two lines, okay? And we know that M1 is equal to the M2, okay? And again, we show minus M1 by A11 and minus M2 by A21, okay? As we know that these two lines have the same slope, we can write the A21 as the A11. And when we try to find the determinant of this matrix, the determinant of this matrix is 0, okay? For this reason, when the determinant is 0, there isn't a unique solution for this problem, and this system doesn't have the solution. Okay. When we have a two simultaneous system of equation, we can use graphical interpolation, but it takes more time compared to the numericals method, and also the resulting solution will not be very accurate. Okay, for this reason, in reality, okay, we are not using the graphical interpolations for solving or finding the determinant. When we have a tree system of linear equations, okay, with how we can find the determinants, okay. For finding the tree system of linear equations, for finding the determinant by Cramer's rule, okay, we can solve the problems in this way. See, we have this matrix of 3 by 3 is meaning we have three system of simultaneous equations, okay, with three variables. This is the matrix of the coefficients minus 1. How we can find the determinant? For finding the determinant of this matrix, we have 3 times, okay, we have to eliminate the first row and the first column. We have minus 2 times minus 4 minus 3 times 5. This is 8. This is 50. For next component, okay, this is the rule. We have minus or negative. What is our variables? Is 5. Now we have to eliminate first row and the second column. We have 7 times minus 4 minus 3 times 1. This is minus 28 and this is 3. And the last one is about this component. We have negative 1. We have to eliminate first row and the third column. Now we have 7 times 5 minus negative 2 times 1. Okay, and this is 35. Negative times negative is positive 2. Okay, and the determinant of this matrix based on the Cramer's rule is 97. Again, for the J components, you have to multiply to the negative sign. This is about the determinant of this matrix. For large N, Cramer's rule is not practical. It takes n factorial floating point operation. For example, if we have a 16 simultaneous linear equations, for using the Cramer's rules to calculate the determinant, would require 16 factorial operation, which is extremely high calculations, okay? And we have a 2.1 times 10 to the power 13 floating point operation. Instead, we use the elementary row operation to rearrange in a form where determinant can be calculated. What is the elementary row operation? The first elementary row operation, you can multiply a row by a non-zero scalar, any number except 0. Okay, that is scaling. Also scales the determinant. The next elementary row operations, you can add a multiple of one row to another row. Okay, and when we are doing this elementary row operation, rotation happened about the root. And the last one, you can swap two rows of a matrix, okay? And when we are using this one, when we reorder the equation, the two row of the matrix, okay, the sign of the determinant should be multiple to the -1. For example, if two times swap the two rows, okay, we have -1 times -1. Okay. Look at these problems. We have two equations with two variables, x and y. And the answer of this system of equations, linear equation, is 10 and 1. If I draw the equation 1, the red line, okay, is about equation 1, and the blue dot line is equation 2. And the purple points is represent the root or the solution of this system. It's meaning 10 and 1. If we generate a new equation by multiple the equation 1 to the 1 numbers, okay, and add it to the equation 2, okay, now we generate a new equation. And as you can see, if we draw these equations, okay, the equation 2 rotates about the purple points, is meaning the roots, and this is the new equation. Okay, this is the new equation of the 2. And as you can see, the solution doesn't change. Okay. For example, look at this example. We have two system of linear equations, okay, and this is about the coefficient for the first equation, and this is the coefficient for the second equation. If we multiply the equation 1 to the s as a scalar value, but again, cannot be 0, and add it to the equation 2, what's happened? The new equations, okay, will be A21 plus S times A11. This is about the coefficient for the x1. And how about the coefficient for the x2? We have A22 plus S times A12. This is about the second variables. And how about the b? We have b2 plus s times b1. Again, this is rotating equation 2 about the roots and doesn't change the solution. Okay, now we have these new systems, okay, and if we select the s, this scalar value, as a minus A21 over A11, okay, what's happened? If I plug the s at these parts, okay, we have A21 minus A21, okay, and as you can see, this element of the matrix turn to the 0. Now we can say we have the matrix, okay, and the coefficient of the matrix of the coefficient now is upper triangular. Okay. This is the upper triangular, and we can, by back substitution, we can find the value of these two variables, okay? If we write this equation, we have A22 times x2 equal B2. Now we have one equation with one variables, and this is the value of the x2. And once we plug this value to the equation 1, we can find the value of the x1. Okay. And this is about the solution of the variables, but how about the determinant? The determinant of an upper triangular matrix is the product of the diagonal elements, okay? And as you can see, once we make the matrix of the coefficient as a upper triangulars, okay, we can find the determinant very easily, okay? And it's the product of the diagonal elements, okay? And once the determinant is not zero, is meaning the system has a solution. All the steps that we did for solving the AX equal B is called Gauss eliminations method. The key idea, rearrange AX equal B into a upper triangular form by using elementary row operation. Then we can easily find the determinant of the matrix of the coefficient and also solve for our variable that is vector of the x. Exactly, we can apply for the matrix 3 by 3 or when we have a tree system of simultaneous equations. Okay, we should try to make a matrix as an upper triangular, and by back substitutions, we can find the value of each variables, and the determinant of this matrix is equal A11 times A22 times A33. This means all the elements, products of all the elements in the main diagram. Let's look at one examples, okay, for this system, for this problem. Okay. For example, we have this system of equation 3 3x1 5x2 minus x3 equals 10. The second equation 7x1 minus 2x2 3x3 is 12. 1x1 plus 5x2 minus 4x3 is minus. Now we have three system of equations, okay? And by Gauss elimination, we try to find the determinant and the value of each of these variables. We learned that for solving this system of equations, okay, we have to write them, these three systems as a matrix and in the format of matrix and vector. What is the matrix of the coefficients? In the first column, we write all the coefficients for the x1. 3, 7, 1. The next column is talk about the coefficient for x2. 5 minus 2, 5. And this is for the third variables, minus 1, 3, minus 4. Again, this is the matrix of the coefficient. What is the vector of the x? The vector of the x, these three variables, x1, x2, x3, equal, because we learned that based on the linear transformation, a matrix times vector, the answer as a vector. Okay, we show the vector in this format. Okay, the vector of the b is 10, 12, minus 1. Now we are trying to make this matrix as the upper triangulars, okay, because we plan to apply the Gauss elimination. By Gauss eliminations method, we try to find the determinant and the value of these three variables. At the first step, okay, I switch the two row, this row and this, okay? See, the first step, switch two rows. We have 1, 5, minus 4. This variable will not switch, okay? And how about the b? x1, x2, x3. For the b also is switch. Minus 1, okay, is going up. And how about the first row? Go to the third row. We have 3, 5, minus 1, 10. And this is the second row. Okay, we know that when we switching the two row, the determinant should multiply to the minus 1. Okay, now we are trying to make this matrix as a upper triangular. Is meaning we have to turn these three components to the 0. For turning, one thing I have to mention, this is the first element in the main diagonal is called pivot 1. Okay, first we have to turn all the elements below the pivot 1 to the 0. Okay, once this element turn to the 0, then we go to the next pivot. Okay, this is called pivot 2 or k equal 2. Okay, then we have to turn all the elements below the pivot 2 to the 0. Okay, now we start by pivot 1. Now we have to turn these two elements to the 0. This is equation 1, equation 2, equation 3. Okay, equation 2 minus 7 over the pivot element times E1. What's happened? We have 1, 5, minus 4. And this is about the right side, minus 1. Okay. How about this one? We have 7 minus 7, 1. What is the elements? The first element for the equation 1 is 1. As you can see, this is turned to the 0. How about the next element for the equation 2? We have minus 2 minus 7 over 1. What is the second element in the equation 1? Is a 5. And This is minus 37 if you calculate. How about the third element in the second equations? Okay, we have 3 minus 7 over 1. The third elements in the equation 1 is minus 4. Okay, and the answer is 31. How about the B? The B is 12 minus 7 over 1. The value of the B for the first equation is minus 1. For this reason, the summation is not. This is the new equation 2. Okay. Okay. If I rewrite this one to make it clear, okay, we have 1, 0, 3, 5 minus 37, 5. This is about matrix A. Again, the vector of the X doesn't change, okay? And how about the right-hand side? We have minus 1, 19, 10. This is the pivot element, and based on the Gauss eliminations, all the elements below the pivot element should be 0. Okay, now we have to try to turn this element to the 0. Again, this is equation 1, equation 2, and equation 3. And how we can turn it, this element, to the 0? Always you have to use the pivot elements, okay? For turning these elements 3 to the 0, we have ET, equation 3, minus 3 over pivot element for this matrix as a 1 times equation 1. Okay, now we can write 1, 5 minus 4 minus 1. And how about the equation 3? The new equation is 3 minus 3 over 1. What is the elements for the first equation? 1. And as you can see, this is turned to the 0. We have 5 minus 3. The second element for equation 1 is 5. And the answer is minus 10. We have, for the third element, minus 1 times minus 4. And this is negative times negative. Positive 12 minus 1 is 11. This is about the matrix. And how about the right-hand side? This is 10 minus 3 over 1. What is the value of the B for equation 1? Is minus. And the answer for this part is 30. Now, if I rewrite the equations, this matrix, we have this matrix. We have 1, 0, 0, 5 minus 37, 10 minus 4, 31, 11. This is for matrix, and this is about the B. -1, 19, and 30. Okay. This is again, this is the first pivot element. And as you can see, all the elements below the pivot now is 0. Now we have to move to the next pivot element. This is the next pivot element, okay? This is K over 2 or pivot element 2. And again, all the elements below the pivot should turn to the 0. And how we can turn it to the 0? Always we have to work by pivot elements, okay? It's meaning we should apply the elementary row operations based on the pivot elements, okay? For turning this element to the 0, we should create the plus 10 to these equations. How we can do it? We can say the new equation 3 is E3 minus this value -10 over the pivot element times equation 2. The reason I mentioned we have to use the pivot elements because if you are trying to turn this element to the 0 by first equations, what's happened? When you try to turn this element as a 0, this value, okay, will add it to these components, okay? And see, when the 0 is changed to another numbers, is meaning we don't have an upper triangular matrix, okay? Now, by using these equations, okay, we try to turn this element to the 0. Okay, we have 1, 5, minus 4. This is for the first row. This is the second row. How about the third row? We have 0 minus 10 over 37. What is the value for the second and the first element for the second equation? 0. See, this element still 0. How about this? We have -10 minus 10 over 37 times the element, the second element for the second equation, -37, okay? Also, this element turn to the 0. How about the third element in the equation 3? We have 11 minus 10 over 37 times 31. If we calculate, this one is 97 over 36. And how about the B? We have 13 minus 10 over 37. And this is equation 2, 19. Okay. And the value of this one is 291 over 37. Okay. Let me rewrite this matrix and vector. We have 1, 0, 0, 5, -37, 0, -4, 31, 97 over 37. Now we can write it. The vector of the variable x1, x2, and x3. And as you can see, during the elementary row operations, these three variables doesn't change it, okay? And about the vector of the B, we have -1, 19, 291 over 36. Okay, now this matrix as the upper triangular, and by backward substitutions, we can find the value of each variables. Okay, for example, if I write the equation 3, because this is equation 1, equation 2, and equation 3. For equation 3, we have 97 over 37 x sub 3, because all the coefficients for the x1 and x2 is 0 or 0, okay? And 291 over 37. When we solve this equation, the x3 is 3. Now we write the equation 2. For equation 2, the coefficient of the x1 is 0. Okay, how about the coefficient for the x2? We have -37 x2 plus 31 x3 equal 90. -37 x2 plus 31. The value of the x3, we find it 3, 9. When we solve this equation, the value of the x2 will 2. Now, if we write the equation 1, we have 1x1, 5x2, 4x3 equal -1. We can say 1x1 plus 5. The value of the x2 is 2. The value of the x3 is 3. Is -1. Okay. Once we solve this equation, the value of the x1 is 1. For this reason, by backward substitutions, okay, by backward substitution, we find the value of these three variables, okay? And we can say the vector of the x, again, this is the sign of the vectors, okay, is 1, 2, 3. This is about the answer of these variables. The next one, we have to find the determinant of this matrix. Okay, we learned that when the matrix as the upper triangular, the determinant equal the product of all the main diagonals. For this reason, the determinant of this matrix is 1 times -37 times 97 over 30. Okay, but if you remember, when I start to solve these problems and try to make a matrix of the coefficient as the upper triangular, I switch the row 1 and row 2. Okay, now I mentioned when we are switching the two row, the determinant should be multiple to the -1. Okay, how many times I switch the two row? Just one time. Okay, for this reason, just one time we multiply this answer to the -1. Okay, this is about switch to rows. Okay, the value of the determinant will be 97. And as you can see, the value of the determinant, okay, in this method by backward substitution is like as the value of the determinants when we apply the Cramer's rules. This is about the Gauss elimination method. Okay. See, this is about all the steps, okay, and again, the determinant is 97, okay, and in some applications, the sign of the determinant is important, okay, and it's not just as a magnitude. And by backward substitution, we find the value of each of these variables. And the Gauss eliminations, okay, is one of the direct methods, okay. We can find the answer of the system of simultaneous equation by direct method exactly if there was no round of error happen during the mathematical operation. And this is the end of the lecture 6, okay, and the quiz 3 covers lecture 5 and 6. Have a good day.